the end. Depending on the clockwise or anti-clockwise, the bending will be there. It may be a hogging or sagging movement. Can anyone draw the hogging and sagging movement in the notepad or do something? I want to know what is hogging and sagging. I explained in the last class, two class before. Hogging and sagging. Hogging means concave, right? It's like a cup, a pond. Pond like bending is called hogging. And then the other one is sagging. So any two type will be getting in any of the loading type. So you have to draw the respective diagram, respective failures profile to analyze the member. Okay, accordingly, I just go back to the previous class that we have done for our calculation of. Actually, I showed that in the last time, but it was not displayed. That's why I'm worried. Oh, okay. Remember, we did it in very first class. We found. Can you see my screen? The Word file. Tutorial week 9. Can you all see this?
Yes.
Yes. Okay, thank you. We did the same case. We found for the member given A, B, D of different cross section, and the loading is here. We found out the value of bending moment and the shear force. It's here. I don't repeat again. You please recall the class or go through the video again. It is there in YouTube. It is accessible anywhere in the world. From anywhere in the world, you can download, you can play and understand how we derive this bending moment and shear force. It was a previous class. We did it. And then I just added one more subsection because you studied already the bending stress. For bending stress, I just added only the small section, which is find out the bending moment if the width of the beam is 5 centimeter. This is 5 centimeter. Throughout, uniform section is given. Determine the maximum bending stress in the beam. It's so simple. The problem is so simple because you are directly given the cross section. The section members are given to you, right? You're just asked the final value of bending stress, right? Immediately you recall your bending equation that you derived in previous class. With that, you are able to answer this question based on the given data. I recall the equation we did. I just showed the equation now. This is the equation we did, right? Can you all see the equation? Can you read? Anyone read? When I call the name. Don't forget this equation. If you want, I can give the equation in the exam, but try to understand the units, the meaning of the factor, or the name of the factors used. Okay. Sadaf Sahid, she's the best in the last test. I think she scored top. Congratulations, Sadaf Sahid. Keep it up. I was wondering because she missed few classes. I was worried whether she could manage, but she got the first in test 1. Okay, congrats again. Sarah Sagib, can you please read for me this equation that I am displaying here?
Yes, miss.
Sigma. Yeah. The PDF file. Can you see the PDF file? Bending yes. Equation. Yes. Sigma is equal to?
Yeah. My
over I.
Yeah.
Equal to M over S equal to E times Y over R. Thank you. Yeah. So this is the relation. You please remember, if you want, I can provide in the formula sheet, but try to understand the relationship. See, bending stress is indirectly proportional to I. I is less, bending stress will be more. Concentration of stress will be more. I is broad, its distribution is broader, very little, because the area is more. You can distribute per unit area very little, so stress will be less. And then moment is directly proportional to moment. When the moment increases, stress will increase. And the lever arm or centroidal distance. I keep forgetting the moment value. Okay, I just hold on for a while because I have to complete this portion. I will post another video. I will post all these video links in the slide, in the chat box. You please go through. Very useful to make you understand what is bending moment, what is bending stress. Come on. This is bending centroidal distance. Depending on the point of interest, maybe you want the maximum bending stress at Y, at certain distance from the bottom, from the top, you can make use of this. If it is just at the maximum value, find out the layer at which it is maximum, substitute the value, you can get the corresponding maximum bending stress. Similarly, is also bending moment, the couples pro that is causing the deformation. This is sectional modulus, okay? Sectional modulus. This one sometimes given in the equation or you have to find out, okay? This is again a formula between this, if you relate this, S is equal to y, if you just bring it down, it will be I over y. S will be I over y, right? You can make out many equations using this, and E is the Young's modulus due to tension, right? When there is a elongation in the member, then the stress over strain is called Young's modulus or modulus of elasticity. Times y is the centroidal distance over radius of curvature or radius, because it is bending in a circular form, right? So the deformation is mathematically found by using the curvature and the centroidal distance from that point and the deformation profile. Okay, let's understand. At the same time I mentioned, when a y is y max, you will get maximum bending stress. Come on, let's make use of this equation here quickly. I just take this relation only because all the values are given to me, right? The centimeter, and then what? And the section modulus, sectional values like depth and width are given to me, so I can find conveniently my section modulus. Section modulus for a rectangular will be found by BH square by 6. This formula also you have to remember, otherwise I will provide in the there are tables you can easily find out from your code books and manuals. All the textbooks, at the end of the textbook they provide you with this formula, no problem. If you want, I will provide in the formula sheet for if asked in the exam. Section modulus, and the moment for now I provide, but I request you to memorize and keep in mind the type of moments, the type of loading, and so on, right? So this is the BH square by 6. Directly we can substitute the section modulus, which is I over y. And then value of B is, the width is already given 5 centimeters. So I change to meter, which is 5. It should be 0.5, right? 5 centimeter should be 0.5. Correct? Yeah. So it's cross section. When I draw, it's a cross section. It's a cross section of that. So I made everything drawn already. Still having one moment. Okay. It's width is 5, so put it 0, right? Put 0. There is 0.5. All of you start writing this question and also do the calculation. Give me the answer, please. Please work along with me. Otherwise, this class will be boring. Just be active. 0.5 is a B, and H is depth of beam. It's already here. Depth of beam is 100. Okay. I'm finding the value at AB, so it is depth of beam is 100. I substitute the value for AB. I draw this. Oh, thank God, I got it. The depth is 10. Depth is 10, and the width. Width I cannot draw here, but perpendicular to the thing is, if you draw perpendicular to, cut section will show you like this. 10 centimeter. This one, 10 centimeter. Depth is 10 centimeter. That's why one I put there. And this is 5 centimeter. Width is 5 centimeter. Okay. Oh yeah, 50. Just very bad, very small amount. One moment, maybe 50 centimeter. Because it's a beam, right? 5 centimeters is very, very small. Let it be 50 centimeter. 50 centimeter. Because with this 5 is so small. Okay, I draw here. Please write down 50 centimeter. So that I have 5 here. Can you find out the answer? What's the answer? SAB. Sectional value at SAB will be sectional modulus, right? Due to the section, the property of the section is given by how many? It's meter square and meter square, meter cube. The answer should be in meter cube. The answer should be in meter cube. How much is it? Quickly. We have to cover the syllabus. Today I'll come up with some drawings automatic so that I don't waste time on the class. How much is sectional modulus? Anyone? Are you working out? Can you switch on the camera and do it? Let me open the file. Where are you? Hey, team is there or not? What happened to team? Are you there?
Yes.
I'm scared now. How do we? Where is my team? I cannot find my team. One moment. Because I updated my version, did some good things, but end up with not so helpful. But I don't know. I cannot find my screen. Okay, find out the answer, please, quickly. Similarly, you can find for BD, the next section. Let me find my team. Something happened. I changed the mode. With the tablet mode is causing me trouble. Okay. I got it. Come on. What's the attendance today? Very good, all of you are joining. What's the answer now? Quickly. Are you doing it? Having calculator with battery and so on? Let me store your attendance. Nowadays is asking the file name. What's the answer? Adult gamma. I start from the beginning. Adult gamma, what is the answer for sectional modulus? We are here. If you cooperate, we can do many questions. Otherwise, we cannot complete. Section model BH square over 6 will give you the answer for how much? This was done in the last class, right? I'm just repeating because that view was not clear. Can you see my Word file?
Yes.
Because I cannot connect with my phone today. Please bear with me. I will keep asking questions today, whether connected or not. I need to check the things. I cannot connect through my phone. What's the answer? Section modulus?
8.333 times 10 to the power of -4.
Why Adil Gamal is not answering? 3 into 10 power? 10 power?
-4.
Meter cube. All are getting the same answer? Okay, proceed. Next one. For the next beam, because the depth is changing, I need to find out separately. I have just substituted the value of what do you call depth only, right? The second one, the depth has like this. The depth is 15. Depth is 15. Okay, not to scale. I just put it like this. 15. Here is the width is 50 centimeter. Come on, find out. What is the answer?
1.875.
Okay, wait. Adel Gamal, you are doing it. All of you switch on your camera. I'm going to take photograph. Switch on your camera. All of you switch on your camera, please. Make it active class. You are not coming to class also in person. Nobody responded to my question whether you are coming to onsite. You're supposed to come to university, government has already passed the rule. All students can come to school, attend in on-site classes. Come on, all of you switch on your camera. Work out the answer and give me quick. Adele, are you there? Or just switch on left? It's afternoon. Yes. What's the answer for the section models here? Others mute. Adele Gamal, what is this answer here? CSPD. For the second section we are finding, isn't it? There's a second section. Depth is given with perpendicular to this wall, perpendicular to this slide is 50. That's what the cross section I drawn here. Okay, cross section actually they can put like this cut section. When I cut here, it will show like this. I take this as x, right? I've drawn here with this. The x-axis is here. Section as x will show like this. The width perpendicular to the screen and then depth 15. You can see. How much is 1 point? 1 or 2?
875.
1.875.
Very good. 8.
1.875 times 10 raised to minus 3.
1.87 times 10 power minus 10 power minus
Minus 3.
3. Okay, correct. Everyone is getting the answer. Okay, you have to make sure. Huh? Come on. I have found the sectional modulus. Now I can conveniently find the stress using this bending stress equation or fractional formula, which relates sigma is equal to mb by sb. Come on. Maximum stress at the end, right? At the end, and we already calculated n to n. The depth is there. Can you give me the answer? We already derived the equation. From the equation we got this formula, right? So we can conveniently substitute the formula. How much is the moment? MBD minus 332.4. 332.4. 332.4 divided by Newton meter, divided by this value. AB, this is for AB. SAB will be 8.33 into 10 power. 8.33 into 10 power minus 4. Now come on, give me the answer, please. This is answer for your bending stress, maximum bending stress at A for AB, for beam AB. What is this answer? Next gentleman. Only one person switch on the camera. What about others? Are you there? You cannot see others. Maybe my computer is like this. All have switched on the camera. Next gentleman, I should keep the attendance with me. Ahmad Nabil, what's your answer for sigma stress? Stress AB. Ahmad Nabil, take his portfolio. If you need time, you say I'm still working. No problem. It's only class. Don't keep quiet. Next. Ahmad Nabil is not here. Ahmad Hassan, what's your answer? Please help. AB, this is a ratio, just a ratio only, right? Is AB we put here? Was already substituted here. They use this area. I have already substituted here. And what is his answer here? Let me write down. I don't know why you're taking long time. Are you using negative?
398.89 megapascal.
3.33 into 10 power minus 4. Okay. And then the answer is negative.
398.89 megapascal.
398.89 megapascal. Okay, next please. Next. Similarly, you can work for BD. We got the stress, just substitute the stress. This is equal to minus 664.8 divided by my stress value is 1.873, right? 1.87 minus 3. 1.87 into 10 power minus 3. Come on, get me the answer, please, quickly. Don't waste others' time. Okay, what's the answer here?
54.56
3, 54.56 megapascal. Okay, done. So it's so convenient because we had an equation, we directly substituted and we have all the values, right? And the question asked you also very simple, because the question is just unknown is bending moment at the beginning that we found already, and the recent question here is bending stress, direct bending stress. Nothing else is asked. So the problem is straightforward. By making use of the bending equation, we can find conveniently. This is our bending equation relation, right? We can conveniently find the unknown answer, right? But what if it is asking for some other parameters to be found in a question? Let's move on. Maybe the second question is, or the similar question was solved here in the second. A wide flange. You are given with a wide flange. Okay. A wide flange was used. A flange I section of standard size. The standard size you use is figure 2. And we also found out last time Sheffield and Benjamin diagrams, right? And then I just added this section. If sectional modulus, sectional modulus, NAL, sectional, okay, let me. Sectional modulus of the beam is 120 meter cube. Determine the maximum bending stress in the beam, okay? And this is the value for, this is a different case, huh? Moment is how much is the moment? Moment you found here, right? Yeah, moment is low, 10 kilonewton, just 10 kilonewton, where the section also very low. With this, we have to find how much is the maximum bending stress. So we can make use of the relationship from the fluxural formula that we derived. Sigma max equal to M max, because it's acting maximum, use the corresponding tag max to max. If it is at some distance, just put sigma only, and then you find the moment at that point or for that beam, right? So you are given with maximum moment, so substitute the maximum moment at that point or for the member, and then the corresponding section modulus. So direct substitution of moment over section will give you the value. What is the answer here, please? In this case, it's a beam with one bending moment, right? Bending stress is given to you. You are asked to find bending stress in the whole beam, right? Due to this moment. Nothing mentioned about a portion or point. What is the bending stress at the beam? Bending moment over bending, section modulus would be the bending stress. Section modulus also given to you. What's the answer here? In Newton or meter square or Pascal?
83.33.
83.33.
33.
All are getting the same answer? Any second answer, wrong answers? To say it's wrong? Okay. If not, let's move on to the question I gave you in the class. I mean, ask you to work out. It's too bad you have not completed. That's why I have to redo it. Can you all see the PowerPoint?
Yes.
The chapter 4, design of beams shells. Okay. I need to do the design after this. Design is nothing but just find out the section member and design of the sizing. Sizing of the member is called design. If you are given size and ask you to analyze for bending moment stresses, it is called analysis. If you determine the dimensions of the beam, cross section of the beam, and it is called design. I already explained to you the difference. Now, in this question, in the figure below, most of you, you close your eyes and you have done it. I don't want to mention them, but you know what mistake you did it. Please read the question twice or thrice. The answer is there already, right? You don't have to worry. You are generating your answer from the given data. See here, the figure below, a Cassian machine part. This is a machine part acted upon by a 3 kilonewton couple. When I say there's a 3 kilonewton couple at this point or end, you should be able to imagine the deformation, how this is going to happen, right? Where's my flow? How this is going to bend, right? Immediately you should say, able to understand the bending, and this will be going like this, right? Just in one line, the member, if I put like this, just going down. You should be able to understand the bending direction. Imagine the bending direction or recall the video you just want to see. But there are many different situations of bending, right? You should be able to understand with the direction of moment or a coupled glide. Right? This the couple here is acting in this direction, and so the member will bend like this. And the sections are given to you. See, conveniently I've given every value for you because I didn't. You are all studied moment of inertia, finding moment of inertia. I don't know, I forgot the term. What parallax theorem? This theorem, that theorem. All are done very well in your statics paper. I don't want to repeat again, asking you to calculate moment of inertia here. Rather, I give you the value directly. You concentrate on analysis and its profiling and then design, not on finding moment of inertia. That's why I have given you already moment of inertia, but most of you are going and calculating the moment of inertia in the question. No need to do. Okay, moment you understand. Knowing E is given to you already. What is E? What is E? Wait, I call the gentleman. What is E here? Ahmad Walid. What is E? Capital E. Ahmad Walid. Ahmad Walid. Ahmad Walid. He's sleeping. Maybe the name is wrong. He's angry. Walid. Are you there or not? What happened to him? Muhammad Islam. What? LC. Muhammad Elshi. Are you there or not? Absent today. Need to be absent. Derek already answered. Kankanala. Kankanala. What is he?
Yes, miss.
Eh? What is he? Young's modulus, right? You said right? A bit louder,
Yeah.
okay. Very good. Young's modulus, ratio between stress over strain. Modulus are always any type of modulus. Young's modulus, bulk modulus, shear modulus, all are stress over strain, the respective stress over strain. Values given, an I value given. Neglecting the effect of fillets, right? Fillet effects, that one you go too mechanical, then you will also understand this minor deformations, but we don't include minor deformations. Come on. Determine maximum tensile stress and compressive stress. Right? Immediately when I say stress, you recall the video just now I showed when a member is subjected to loading, how the tensile and compressive failures will occur in a member. Just understand that, may recall that you are asked one more term here, radius of curvature. Then you should do a bit of recall the derivation we did in the class, a bit of drawing and understanding of the deformation is required here. Okay, this is the couple, and you are given this. Okay, go to the diagram. Diagram also important. After reading the question, please read the diagram. Some information are there in the diagram. I'm supposed to give, but I just tested your focus, how much you are focused. But nobody did it correctly. Did I pull this gentleman here? Somewhere here. Where is this? Oh, gone inside. Okay, leave it. It should be here. One moment. I don't know. Okay, leave it like that. I will mark again. I just mark myself. This one point, this point. Okay, red point. You are given with the section. When you cut the section, the cross section will have width of flange width of 90 and overall depth of 60. And this one, the web depth is 40, flange depth is 20, and thickness are all not given, but it is. Let's see whether it's useful or not. And the flange width is given 30, and so on. And then you have one more value which is center of gravity. The centroidal distance is given to you already. If I say CG is this value, centroidal distance, I have to pull this a bit. Okay, the centroidal distance is given to you already. CG, point CG means what? Center of gravity or centroid. Centroidal distance of the point to which the net force or total force is acting is given to you already. The distance from this point to this point is 38. If this is 38, you can find this value, right? How much is this? This is your point A, right? The point A. Answer me quickly, anyone? This is A. This is A and this is B. Okay, let it be. I think it is there in the diagram. B, okay? B. When I give this is 38, right? This point is 38. How much is the value from A? Centroidal distance from A, this value? Answer me. How much is this distance? I don't know why I'm not getting this black. Black. How much is A? Point from A. How much?
22.
Okay. Very good. 32. Huh? Remember this
22.
one. Yeah, you may be using this one later. What's happening? That's why we need a board. Use board. 22, right? 22 mm. Because already 20 and then there's 2. Balance 2, right? So distance between this and this is given by this is the central distance of A, point A, and this is the central distance of point B. 38 is a central distance of point B or the bottom flange. Okay. And remember these conditions. These are all given to your D. Somebody gone to calculate, when I say check the answers, you went to calculate all the values like CG, I is already given to you. Come on, let's work out together with me. Next slide. Okay, you are asked to find out these 3 values, right? Maximum tensile, maximum compressive stress, and also radius curvature. For these 2, you can use the formula, but you need to understand where the radius of curvature is lying. For this purpose, I have brought down here, and this one no need, you already given. Centroid distance is given to you, 38, and I value is also given to you. The strategy of getting the solution is write down all the formula that you are going to use. And this data already given. If not, you have to use this formula to find, right? But in this module, the whole module, I will provide you this data. You concentrate on others. Apply the elastic fracture formula to find the maximum tensile stress and compressive stress. So use this one. M is the maximum here. You can take it to be maximum. And then My also max. When I say this one is max, this is also max. Automatically, it will change to max. You can do it as a subscript. Okay. All right. And then because you need max, you need to substitute Y max. Find out where is Y max. Can you tell me where is Y max? Is there by letter also you can say, by location also you can say. Costar, where is Y max lying in the flange? I mean, where is the Y max lying in this section? Y max in this flange section. Where is the Y max lying? At what section? Is it at the top and bottommost or somewhere else? Cosar, Y max, maximum bending stress. I just guess. I'm going to draw the diagram, don't worry.
Is that the
Guess.
top?
Very good. Topmost and bottommost will have the maximum value. Very good. Right. A and B, right. So by substituting the corresponding A and B, you will get the answers for corresponding bending stresses. Good. Calculate the curvature using this. So I have given in the same equation. If you see the bending stress equation, you also have the R value, right? Same thing we can use here. It's a 4.9. Same equation. I just relate whatever the data I have. I need to calculate R. I have M. I have E. In the question, E is also given. E is given. So I try to use the relations that are given to me, right? A relation which has the data that is known, which is 1 over R equal to M over EI. These are the formula we are going to use. That's a strategy you're going to adapt. A concept you're going to, hypothesis you're going to adapt. Come on. Let's draw the diagrams. To avoid time, save time, I will draw before the class. This is a section according to the bending, right? When it is the bending is causing like this, it will tend to bend like this. The deformation will take place like this. Unlike the last case, it will tend to bend like this because the bending is in this direction. If it is in this direction, it will go inside. This flange will go inside. It's a hogging. Now it's a hogging. What do you call? One moment. Sagging. This is sagging, right? Hogging is inward. Sagging moment. This is sagging moment. So you have like this. When you draw the diagram, you will have the profile. Either you can put it on one direction or opposite direction also okay. Doesn't matter. Right. When you draw the profile, the Y max will start from here, right? The maximum tensile stress, because the fiber has extended, right? So I will plot it as a tension here, maximum. Keep on reducing until the centroidal distance, centroidal axis at center becomes 0. It's not to scale, it is very small, please understand. And then at central axis becomes 0. Then start the value of plotting the value of compression. It can even be like this in this direction, but direction of compression should be in opposite directions to show it is compression. You can even plot it this way, like the one in the video. Either this direction or this direction you can put. So the diagram of compression is in this way. From neutral axis slowly increasing to the bottommost or extreme layer of the section. Okay, this is what the diagram shows. To find R, the location of the R, you mark on the center of gravity. Just complete the circle, the curvature. Then you can get the center. From the center to the fiber, the end of this ring will be R. And you have A and B, where you can get your maximum values. This A to G, CG will be, how much is A to CG? Anyone? Just now we plotted. This is going to give me the distance for Y max for compression. And this is going to give me the distance for eraser. And this is going to give me the, just imagine in what direction. Actually, I should not leave until this point. Perpendicular, this section is perpendicular to the slide. Imagine this to be perpendicular slide. So the distance from here to here is better I show here. Here to here will give you the maximum tensile because it is this is tension, sorry. This is tension, and the bottom one will give you the compression. Okay. Can you do this calculation? Start from here. Or if you write this slide, write down this slide. It is not there in your slides. Come on. All of you start writing down this slide. I mean the formula. Can you work out for me quickly? I'll give you 5 minutes time. I think it's more, only more for you. 5 minutes. Now this 18. I will ask at 23. You will have to start with the design. Please help. So first you find out this value, maximum tensile stress, and then maximum compressive stress. I will ask gentlemen, but ask what? More tasks. Oh, Gultan is answering. That's I just exclude his name. Now Ismail going to give me the answer for number 1 stress. What is this? Tensile stress. Please take it sportively and then do it because you are spending few minutes with us weekly. Make use of it. I'm sure it is going to be a good training for you to do more calculations over the weekend. Now, come on, give me the answer for maximum tensile stress. Use this formula, Y max, sigma max, and take the distance for the compression centroidal distance. What are you doing, everybody? I just keep it here. Good. Must be step answer only. Are you there, Noah? Ismail shouldn't be your name. Nawal, I think. Girl. What's the maximum compression stand? Tensile compression. You give me tensile only. And then in case if next gentleman, Ongzen, can you give me the tensile compression value? Compression stress how much?
131.3 megapascal.
So these are all the answers. What happened to novelist mind? Slept? What are you doing? Absent. So sorry. Get back quickly. Otherwise, I will give a absent. See, this is the stress for compression and tension. Tension, compression. See the tension? You go and imagine. Can you imagine the value? Tension is here, compression is here. Because Y is less, the value is also less. Y is more for compression, the value is also very high. See here, high. Okay? Because directly Y is directly proportional to stress. So this is the value. You can yourself compare whether your answer is correct or not. Are you all getting this answer?
Yes.
Okay, good. Next gentleman, Raymond. Raymond Rakyan, come on, give me the answer for or. I'll just guide you. Oh, did I give answer? Oh. Are you getting this answer? Raymond Rakyan.
Yes, miss.
Oh, very good. Then clear. Matter clear. Everyone follow this. I have to remove this. Actually, I used R. Right. Lastly, we got all the three answers. Number one is stresses, right? Maximum tensile and compressive stresses got, and then finally the R value, which is 47.7. Come on, think on this. Hope everyone has completed. Time up already. Do we need one more minute? Good. Let's rethink, reflect on this. Justify your answer, it's important. The applied couple lies in the plane of symmetry for dissection, resulting in symmetric bending. The applied couple lies in the plane of symmetry for dissection. Okay, resulting in symmetric bending. Unsymmetric bending would occur if the couple is applied in another plane. This is not covered under the scope of this module. So you're only seeing the good diagram there. Symmetric bending, it is not applied in a different way, like at some distance away from, or at some distance inside, right, inside the beam. So the type of values or type of moment that is causing is very symmetric, loading symmetric moment per moment, or load per load times area, load times the distance. Hence, you will have symmetric bending, or when you cut, it will equal halves or equal. It will divide the section into two into equal halves. That's why we call this as a symmetric failure or symmetric moment, resulting in symmetric bending. Okay, non-symmetric or unsymmetric bending types is not covered here, but thorough of these types of bending at the ends or at the middle point or at the support and so on. You find out many calculations similar to this. I may ask one such question in the exam. Okay, I stop here. I put some videos later. You please watch at your free time. Let's continue with the next section, subsection of this chapter, which is design. Give me a minute. I open the slide for you. Any question in the calculations? Design of beams. Can I close the other file? Practice similar questions. Okay. And do some theory first, and then we move on to calculation of the or design of the members. Determine the dimensions, determine the depth, or all the types of questions to be asked under this section. And width, front signals, and so on. Okay. I have few theory slides. Let me go through that. Okay, let me share the slide. Can you see the slide? Okay.
Yes.
Okay, thank you. Design of beam to resist both bending and shear load, right? We cannot separate when you want to design a member, you have to design it for all the net load or total load acting on the member. Hey, when I say this one, please recall the situation happened last week. I think 2 days before or last week. I've forgotten the date of this news. Do you know there was a bridge in Australia or Europe? I don't remember exactly. I think in Australia there was a bridge in Australia collapsed due to radiation. Do you know that? Did you come across this news? In all our codes everywhere so far in the global design or you take any types of codes, design codes, we are considering the major types of loading like live load, dead loads, and then the lead load means self weight of the member, and then the wind load, lastly seismic load or earthquake load, right? These are the four types we usually consider for our design. But there was a failure of a collapse of a bridge due to radiation, effect of radiation. Right now, it sounds that you have to consider other type of loading, other type of failure, like this radiation due to radiation. We do not know whether radiation from the environment or radiation from the rocks, the isotopes beneath the ground. We do not know. We have to identify the where, but it was said in the news that due to radiation effects, the bridge got collapsed. So it says that it reflects on redesigning or considering the radiation types of failures or the type of loading that is causing failure in the members. So like this, you people are going to face many challenges in the future design. So you must try at least few types of questions that we are giving you every class and that are there in the textbooks. Thoroughly work out, and if there's any question, you ask immediately. Right? I don't know much about this type of this news. If you have a chance, you please read about this information. Failure due to radiation effect, not only loading or seismic loading or wind load or other types. Right. Design a shaft to resist both bending and torsional moments. So all of you know that if there is any compression or tension, you have tension and bending. But the shear, the third type of failure, which is shear load, will cause automatically the torsion load or torsion moment. Okay, shear will cause torsion moment. Normal tensile and compression will cause or bending will cause bending moment. Okay, prismatic beam design. Prismatic, see the term itself prismatic. Prismatic means geometrically similar. Again, it's a symmetric member. Prismatic again, referring to a symmetric member. The cutting section at any plane will read equal halves on both sides. We are going to find number one is a prismatic and axially loaded. Once you're thorough, you can modify the values, the lever arm, to find out the corresponding non-prismatic section. Why we are not taking non-prismatic section into consideration? They're all non-linear. It is very difficult to model or analyze using the simple arithmetic methods or the static equation that we are using. You really have to go through, for proper design, you really have to go through what do you call the matrix analysis using MATLAB or using software, using StatPro, and using softwares only you can analyze thoroughly the failure pattern, the corresponding design will be appropriate. But when you do manually, you can only get approximate value. That is one thing. When you at your job place, you will be designing for non-linear and non-prismatic sections, right? That is quite common in every design. But by making use of the software, understanding the basics, the formula involved, by making use of the software, your complex problem will be conveniently analyzed and designed. Right. Let's understand thoroughly about prismatic beam first. A beam is designed based on the strength so that they can resist the internal shear and moment developed along their length. So bending is always along their length or along parallel to the longitudinal direction of the member. Although some beams may also be subjected to axial force, the effect of it is negligible compared to others. Ensure that the bending stress and shear stress do not exceed the allowable bending and shear strength. Okay, allowable means the material. In all cases, we are designing according to the material allowable things or material strength, not exceeding. Failure, there is no failure due to what do you call that? Factor of safety is good. Factor of safety is always maintained above 1. Then you are designing for not exceeding the allowable bending. A bending design requires in beam section modulus, right? I over C is Y. Hence, using the Fletcher formula, sigma is equal to my over I. Later, I will change the notations. It is my over I. We can have the formula as section modulus equal to m over sigma. M max is determined from the moment diagram and sigma allowable is specified in a design code. When you choose a material, aluminum, alloy, or any type of material, iron, or any type of material you choose, it will give you the design value, allowable or strength value, bending stress value from the code book. We will give you the value first in the exam, or I provide the table, attach the table together with the question paper to choose the value. We'll do both.
Excuse me, Miss.
Yes,
Which slide are you in now?
prismatic beam.
Slide number 2.
I don't remember. It's prismatic beam design.
Because we are still in slide number 2. Design of beam and shafts.
How come? Let me check.
Yeah. Now changing already.
Oh, God. Yes, I shared already. Okay, come on. Thanks. You can see prismatic beam design.
Yeah.
Good. I have given you the information about bending. Bending happens parallel to the longitudinal section, and you have your going to design for that will directly come here. You are going to design for allowable value. Means factor of safety will be always more than 1. You're not going to design for a failure member, right? In that case, you can still use the fluctual elastic formula within the elastic limit. That means you are designing within the elastic limit. Still you can make use of the formula that we derived last class. From there, you take the equation for section modulus as moment over allowable stress, where m is the maximum moment and sigma is the allowable stress, which can be taken from code corresponding to the material that are asked to analyze and design. Okay. In exam, if the value of sigma allowable will be given to you in the question itself, or I provide a table, a page, copied page from the code book for you to choose from the table for the stress value, unit stress value. Right. Prismatic section will be like this. Hot rolled steel sections are mostly used. The appendix A and B, I will show you. You're all using the code book, the same code book, right? Ibler. If you see this appendix B, are you having it right now? Can you go and check? Otherwise, I will, at the end of this slide, I will show you the appendix B. We'll have all the section values. We will go once again to check, don't worry, because I brought the section already here. AISC, American Institute, have standards W460 times 68 is showing like this. Height is 459, okay. End to end height is 459, approximately 460, right? The small mm, right? Small mm that is missing, 1 mm missing will be due to the material, right? Sometimes they cannot get a very clear cut dimension. So around this value will be designed, and the weight is equivalent to 0.68 kilonewton over meter. When I say 0.68 kilonewton over, you are able to imagine the value. Okay, come on. The flange looks like this. One moment. Flange look like this. Thickness of the flange is 15.4. Thickness of the web, this is called web, this portion is called web, this is called flange. Top flange, bottom flange. Thickness of the web is 9.14 mm, and the section, this is called section. What section means? You have to say like this, W460 times 68, right? And the one of the codes will have like this prismatic beam section. We'll have all the section word names, area, depth, web thickness. This is all manufactured. This is already manufactured, and if you're going to use it in your site, it will be supplied to the site, right, to the contractor. You will have different sections, and then you can choose based on your design values for adapting in your construction. Right. Prismatic beam section. You're going to design this one like this, right? Given the load, you will choose from here. Vice versa, given the load, you are asked to find the stress. A stress is given, and you will be asked to find the section modulus corresponding to the moment produced. Okay. Prismatic beam design. Wood sections, it is also covering the wood section. Remind me, I have to stop class at 45. Have you read my messages at the chat box? Remind me at 45, because last time I got confused in the class starting for the other one. That's why I'm strictly stopping at 45, and then on Friday we will extend it. It's not fair to start early, that's why I postponed to the end of the session. Okay, and the other class also I cannot start early because they are starting at 9 o'clock. Already for foreigners, especially the Middle East people, starting at 9 is difficult for them. If I do prepone again, I cannot manage. That's why I'm cut short at today's class every Wednesday class at 1:45, and then extend Friday class until 12:45 instead of closing at 12:30. Please note this. Okay, wood sections are listed by National Forest Products Associations for use in the design. Nominal dimensions in multiples of 25 mm or listed. Example 50 times 100 mm. Actual or truss dimensions or smaller being 37.5 mm by 87.5. Dressed means clear surface. No, they want a white and smooth surface. They do some smoothing. What do I forgot the name? Filing. The filing. They do some filing at the side. End up with 37.5 and 87.5 mm. Reduce the section at the side. After loading, they will do filing to fix having a smooth section, uniform section, and for bright color, whatever the requirement of the site. By that, the value will be reduced due to filing. Just crush it, file it at the site to get this dimension. The reduction in dimension occurs in order to obtain a smooth surface from lumber that is rough sawn. Right? From although the manufacturer ends with this, manufacturer clearly in the beginning also see here 459, 460 turns to 459. Although they try to reach 460, they cannot reach 459. And coming to site, due to loading and unloading, transport, the lead time taken, due to all this effect, there may be slight change. To neutralize or to balance out throughout the section, they do filing at the site, end up with some section reduction at this point at the site before using. So you have to make this note. Obviously, actual dimensions are used in stress calculations. So you can use the actual one in stress calculation. You will be given, for now you will be given, but try to understand these variations that is happening, minor variations that is happening in the actual design and the manufactured one. Right. Prismatic beam design. Built-up sections is constructed from two or more parts joined together to form a single section. Right. And this is welded because welding, they put the welding, different types of welding. If it is welding, there is some material here, like a fillet, filling with some fillet. With that, this web is joined to two flanges. In this case, bolt and rivet, bolted. This is bolted with the you forgot this term. This one, fillet. I think fillet and the bolt. They use a fillet to connect both, and onto that on top of the fillet they put the bolts. Okay, on top of the bolt they put the bolts. Bolts are connected. See, these two bolts are supporting the flange, the web, and this one supporting the flange and this web. Like this section may be either welded or bolted. Wooden hollow. Sometimes the member may be a hollow one, box type, hollow box, or filled type, Gulam beam, right? Gulam beam. You see here the variations. It's all depending on the purpose and the design. Procedure. Shear and bending moment diagram. All of you know what is shear and bending moment diagram. Have any questions so far? Right. Determine the maximum shear and moment in the beam. Often this is done by constructing the beam's shear and moment diagrams. For built-up beams, shear and moment diagrams are useful for identifying regions where the shear and moments are excessively large and may require additional structural reinforcement or fasteners. Why we need this shear and bending moment diagram? We need to know where is the maximum, where is the worst section, right? The failure section, or where it is to be reinforced, right? Wherever there is a hogging and sagging, like you have a hogging, by providing the reinforcement, you can, if there is a bending like this, right? If there is a bending like this by the beam, by providing the reinforcement at the bottom, it can be straightened, right? It can still bear the loading, right? Due to loading, if it is bending like this, by providing the, if you see this is the extension, right? The elongation, by providing the steel rod at the bottom, you can keep the member in a good position like this. Okay, I will show you the diagrams, proper diagram and videos so to understand better. Now, what are all the stresses? Number one, normal stress. If the beam is relatively long, it is designed by finding its section modulus using Fluxo formula. We have already seen this one. This and this also already seen. If roll seal sections are to be used, several possible values of S may be selected from the tables. Of these, choose the one having smallest cross-section area, since this beam has a least weight and is therefore the most economical one. Right. You can also test with the different values of sectional dimension. Go directly to the table. I will explain about the table later. It's not here. Right. You can also test and see by changing the sectional value, whichever is appropriate according to the bending moment and shear force diagram, shear force values that you are finding. You can change the dimensions, right? You can change the dimensions of the sectional value to suit the required bending moment, to support the required bending moment. Prismatic beam design. Make sure that S is slightly greater than S required. As usual, the factor of safety applies here. And the required should be more than the selected, right? Like what do you call it? The member should be good enough, or member should have more section value than the design one, so that arching moment created by the weight of the beam can be considered. Shear stress. Normally beams that are short and carry large loads, especially those made of wood, are first designed to resist shear and then later check against bending stress requirements. Using the shear formula, check to see that allowable shear stress is not exceeded. Allowable shear stress is not exceeded the designed one, which is tau max is equal to VQ. V is a shear force, VQ over IT. I will explain about this formula in the next class, because I need to do a short derivation. So the maximum allowable will be like last time we did a factor of safety of 1.5. You can still follow 1.5 as a factor of safety for the shear stress and also for the normal stress. Okay, you can use the factor of safety to be 1.5. Okay, coming to the fasteners, adequacy of the fasteners. I will explain about this one in the next class. While doing the calculation itself, I will explain how to determine the values of allowable and applied or the required values. Okay, that's one. Adequacy of fasteners. With this, I ended the class already 45. The adequacy of fasteners used on built-up beams depends on the shear stress and the fasteners that can resist. Okay. In addition to the member property, the fasteners, whether it's welded or bolted, the bolts and fillets connected to the member will also have respond to the loading. That's what we did in the beginning of the class. Like 2-3 classes before, we found the strain due to pin and the links and so on. Especially the required spacing of nails or bolts of a particular size is determined from the allowable shear flow, which is equal to VQ over I, calculated at points on the cross section where the fasteners are located. Right. That's why we need to determine, if you're asked to find out the shear stress, determine at the fasteners first and then for the whole member itself. With that, we are stop here. Any question you can ask me. By doing calculations, by applying these principles in the calculation, you're able to understand better. Okay. Let's stop here. We'll continue in the next class. Any question for today? Let's stop recording. Already 47.